And now we can have a second look on this task 21 that we already solved with the help of a delta star transformation to get rid of this resistor R5, and finally ended up with this equivalent resistors between the nodes A and B. And so now the idea is to do it once again, but now with the help of star delta transform. So where can we find a star in this circuit that we can transform into a delta? Yeah, so let's label the nodes here once again. This is what we call C and this is what we call D. And so now a star would be, as mentioned, A, C, D, and B. Yeah? For a star we need 4 nodes, so this would be a star, even if it does not really look like this, but let's draw it like this. So this would be a star circuit that we can transform into a delta, or this connection here like this way. So let me take a different color. This would also be a star that we could use, but of course we will only choose one of them, and let's choose the top one. Okay, so I will once again redraw the circuit, and so now we take this star and transform it into a delta. So on this side here we still have our node A. So this is A, and from A we then have one resistor in this delta that goes all the way over to B already. And then we need 2 resistors that connect this point with D. Maybe I should do the D a little more down below, like here. So this is D. And so from our star we need to have, if we convert this into a delta, one resistor that goes this way. This does not look too nice, but it's okay. This looks better. And we still have the old resistors R3 and R4. Okay, so this is R3, this is R4. And this resistor here now I will call RAB. This is what I will call RA and D, and this is RB and D. And yeah, then of course we need formulas to find RAB, to find RAD and RBD from the star data transform. And we will do this in a second. And when, of course, we need to have some formula that, yeah. And now it's a bit difficult. So this is just the one that we need in our transform here. At the end, we would still need try to find RAB, the equivalent resistance between these 2 nodes here. And let me also draw some soldering dots here, points that connect the branches with each other. And so, yeah, at the end we would need to find a formula here for this equivalent resistance. But at first we look at the transform. Okay. So what do we do? You had some idea?
Yeah, we've got the formula in the...
We have the formula in the lecture slides, exactly. So we take a look back into the lecture slides. There were here somewhere. So this is now the conversion from star into delta. This is the way how it's written with conductances. And then you see it's the same as we had before, just with conductances. So if we want to have the conductance of the resistor that is connected between nodes 1 and 2, it's the product of the two conductances that are connected to these nodes in the star connection divided by the sum of all the three conductances. And so we could now convert all our resistors into conductances, use the very same formula that we used before here, right? This was the same thing, but just with resistors, with the other way around. Or we could do this additional step, transform it back into resistors, and then we get these equations here. So the resistance between the two nodes, or between two nodes in the delta connection, is the sum of the two resistors that are connected to this plus the product of the two resistors divided by the other resistor. Can I memorize this? No. Do I have to check it up all the time? Yes. And if we check the Wikipedia page, so they have a slightly different formulation here. But if you would check, if we, at the end it's the same. If we divide R1 by R1, we are left with R2. If we cancel here one R1, then we get R3. So we have R1 plus R3, and then we have R2 plus R3 and then plus R2 times R3 divided by R1 by the other resistor. And the schematic is unfortunately far away from this formula there, but okay, it's the same that what we have here. Okay, so maybe I should have just copied this, but okay, we will rewrite this for our problem here. So if we want to get this resistance here that connects these two nodes A and B, then we need to have the resistance at the one node plus the resistance at the other node plus the product of the, it should be R2 exactly, and then plus the product of the two, R1 multiplied with R2 divided by the other one, which is R3. It's always a challenge to speak and write at the same time. Okay, so then we have, we can continue with this ARD that connects A and D. So we need to check, okay, what is connected to A? This is once again R1. What is connected to D is R5. And then we need to have the product R1 multiplied with R5 and divided by the other resistor, which is R2. And then the remaining resistance is this one here that connects B and D. And what is connected to B is R2. What is connected to D is R5. And then we have R2 multiplied with R5 divided by the other one, which is R1. Okay. Next step, inserting values. And luckily here this is simple, so this is 1 plus 2 is 3, and this is 2 over 5. So maybe I will just write it like this, that it is 3 plus 2 over 5 ohm. And so for our next formula, it's probably a good idea to write it down in a simpler way. So if we expand 3 to the denominator of 5, it's 15, and 15 plus 2 is 17 over 5 ohm. Okay, so then 1 multiplied with 5 is 5, so we have 5 over 2. And we have additional 6. And 6, if we expand 6, 2 over 2, it's 12. And 12 plus 5 is also 17. So here we get 17 17 over 2 ohm. And here we have 2 times 5 is 10. And 10 plus 7 is 17. So we have 17 ohms. So it's, yeah, it's always something with 17, but just with different denominators. Okay, so now we have successfully transformed our star circuit into a delta circuit. Next step is we need to have a formula for the equivalent resistance of the circuit between the nodes A and B. Yeah, this is not the same resistor as here. It's the total equivalent resistance. So what do I need to write down here? So at first we can start with RAB dash, this one there. Okay, so and this is in parallel to yeah, so then we have, if we start on this side, we have RAD in parallel to R3, and this is in series to RBD in parallel to R4. And okay, the parallel connection is like a multiplication, so this is what you would calculate first. So I don't need this parenthesis here really, but before calculating this parallel circuit, for sure we need to do this plus calculation there. And so now interestingly, if you check this, if you compare this with what we did here, it's the same structure of the formula, just that each plus turns into a parallel connection and each parallel connection turns into a plus. And this is also shows this kind of duality between these two circuits or between these two problems. Okay, so the next step is we just insert the values. So here we have 17 over 5 ohm. And this is in parallel to RAD is 17. Yeah, I will just rewrite it and then we will calculate it in Octave. So parallel to 3 ohm. Plus, and RBD is 17 ohm parallel to 4 ohm. Okay, and so then let's look for the Octave window. We still have this parallel function there, so the parallel function of 17 divided by 2 and 3 gives us 2.2174 ohm. So here, yeah, you could almost do it still by calculation in your head, but as said, not at this time of the day. So 17 and 4 gives us this 3.2381 ohm. So now the series connection of this and then in parallel to the last one. So yeah, maybe I can copy here a bit, plus this parallel thing of 17 and 4. So this in total gives this, and so now at the end we need to have this in parallel to 17 over 5. And this should be our total equivalent resistance. So it's once again 2.0946, which perfectly makes sense because this is also what we calculated before. So we can make a check mark and say, okay, it should probably be correct because, yeah, it would be quite a freakish coincidence if we would have done the very same calculation mistake in this way and in these formulas as in these formulas here.